Hello again. This time we're going to talk about sampling distributions. Suppose that we put this into a story. Suppose that we have a population of people that commute to work, and we know that their commute time has an average of 38.8 minutes and a standard deviation of 11.4 minutes. And let's assume that we've looked at this data and convinced ourselves that the distribution of commute times can be treated as normal. If I pick one person out of this population and calculate something like the probability that that person's travel time, and will that x be the travel time, is say less than 35 minutes, then we know how to calculate that because we know the distribution. The mean is 38.8, the standard deviation is 11.4, and we can use Minitab, and we can calculate the probability of x being less than 35 minutes. And I did that a few minutes ago, and that probability is 3, 6, 9, 4. So there's about a 37% chance, if I pick one commuter at random, that his commute time or her commute time will be less than 35 minutes. Now suppose that instead of picking one person, that I pick a sample of, how many? Let's say n equals 36 commuters, and I compute a statistic. I think I misspelled statistic there, but you know what I mean. All right, so what is a statistic? Anything that we compute from the sample, by definition, is a statistic. So the kind of things I could compute on my sample of size 36 would be x bar, the sample mean, or I could compute S, the sample standard deviation, or I could compute R, the sample range, and we could go on and on and on. The high value in the sample would be a statistic, the low value, the median. So those would all be things I could compute from a statistic. If I went back and took a different sample of size 36 and computed the same statistic, let's just suppose that it's x bar that I'm computing, just for the heck of it. The second time I took a sample of size 36, x bar would not be the same. So I would expect that x bar 1, that would be the first time I sample, would not be exactly equal to x bar 2, that would be x bar from the second time I sampled, would not be exactly equal to x bar 3, x bar from the third time I sampled, and so forth. That is, x bar will be exhibiting variability, and it's going to have the properties of a random variable. All right, could we say the same thing about, suppose that the statistic we were computing was S instead of x bar? Yeah, the first time we'd compute S, we'd get a standard deviation. Take a different sample, you get a different value of standard deviation. Take a third sample. Again, I would expect a third value, and so forth and so forth, for any sample that we want to, any statistic we want to compute on a sample. So these statistics, if I collect them over and over and over, exhibit the properties of a random variable. Now, while I can do this for any statistic, let's for the time being just concentrate on x bar. So let's make some statements here. X bar, that would be the sample mean. Maybe I'll write that down. X bar, the sample mean, has the characteristics of a random variable. It is a RV, not an RP, not a recreational vehicle, RV, but a random variable, RV. Now, if it has the characteristics of a random variable, it has a distribution, of some kind. It has parameters of its own. It has its own mean, and it has its own standard deviation. So we can talk about x bar having a distribution, and we can talk about mu x bar and sigma x bar. Now this time I'm putting the subscripts on there, the sigma x bar and the mu x bar. I said that backwards, but you see what I'm saying. I'm putting subscripts on because we have other values of mu and sigma. We have a mu and a sigma for the population. So these would be for our sample. So these are the mean and the standard deviation of the sampling distribution of the random variable x bar. Now what about the distribution? Well, sometimes we won't know the distribution, but often we will because of a wonderful result called the central limit theorem, abbreviated CLT, central limit theorem. And the central limit theorem, you should read it out of your book for precise language, but roughly it tells me that if I take samples, all possible samples of the same size, and if that sample size is greater than about 30, then x bar is going to be normal, even if the population isn't normal, and mu x bar will be exactly the same as the mean of the population, and sigma x bar, the standard deviation of x bar, will be equal to the population standard deviation, I'll put a little x there, divided by the square root of the sample size. So that's a lot to absorb. We've gone over the 5 minutes that I usually set as a limit. So let's end here, and I'll come back in just a few minutes and we'll take a look at a particular example. Thank you very much. Be back with you in a moment.